When you've completed this lesson, you should be able to do the following. Simplify an expression, rearrange formulas so that one variable is isolated, and substitute into formulas and solve for unknown quantities. These are skills that photonic technicians will use often. They'll use algebraic expressions that have variables, constants, and operations. You'll solve for desired variables and constants in those expressions. And you'll substitute known values and evaluate these expressions. Let's look at a couple of examples here. You may need to solve for the wavelength lambda in the expression delta E equals hc over lambda. How do you get to that lambda down there in the denominator? Or you need to find the mirror curvature r sub 1 in the formula g1 equals 1 minus L over r1. Again, how would you get r1 all by itself over on one side of the equation? Well, we'll find out in this module. Here's an example problem that photonic technicians solve, measuring an argon laser cavity with a length of 50 centimeters, and you know the reflectivity of the two mirrors is 0.998 and 0.9575, and you measure the loop gain to be 0.969 with a cavity loss of 8%. Well, you have this wonderful formula. The loop gain, G sub L, is equal to the product of reflectivity of the two mirrors times the amplifier gain squared times 1 minus the round-trip cavity loss. But you don't need the loop gain, G sub L, you need G sub A, amplifier gain. How are you going to solve for amplifier gain, G sub A? In this module, you'll learn how to do that. In mathematics, a formula is a way of using symbols to write a sentence. So consider these. You may remember the formula P is equal to 2L plus 2W. Well, that is really the same as the sentence, the perimeter of a rectangle is the sum of twice its length and twice its width. Or I is equal to PRT. The simple interest earned is the product of the principal, the annual rate, and the time in years. And it's much easier to write just I is equal to PRT. Or here's one that you've surely seen. C is equal to pi times d. That's the same as the circumference of a circle is equal to the value of pi times the diameter. Isn't it much quicker to write C is equal to pi d? But what if you wanted to get one of the other variables out there by itself? You'd have to do some manipulation with the algebra, and that's what you'll learn to do in this module. Which operations have to go first if you're going to evaluate some of these expressions? Well, we have a cute little saying to help you remember that. Please excuse my dear Aunt Sally. Now, hopefully by the end of this module, you'll remember this saying and you'll refer to it often to get the right order of operations. The P in the please excuse my dear Aunt Sally stands for parentheses. That is, first evaluate everything inside the parentheses, brackets, or other grouping symbols. Next, we have E for excuse, which stands for exponents. Next evaluates exponents in powers. M and D for my dear stands for multiplication and division from left to right. A and S stands for addition and subtraction, which is the last thing that you should do in an expression, from left to right. So that finishes the please excuse my dear Aunt Sally. Let's look at an example of how that works. Let's consider the expression 8 minus 3 times the parentheses of 5 plus 2 to the 4th power, close parentheses. Which operation should we do first? Well, the please excuse my dear Aunt Sally tells us that the first thing that we need to do is look at the parentheses and evaluate what's in the parentheses. So inside the parentheses is 5 plus 2 to the 4th. And which should we evaluate there first? We should evaluate the 2 to the 4th first because it is the exponent, which is the next thing after the parentheses. And 2 to the 4th is equal to 16, so we simplify the expression to 5 plus 16 inside the parentheses, but we're still working inside the parentheses. Now we need to do that addition, which is the only operation left. So that gives us 5 plus 16 is 21. The next highest priority is the multiplication of 3 times 21. So that gives us 63. So finally, we're ready to do the last operation, which is a subtraction in this case, and we'll end up with a negative 55. Now, when working with equations in algebra, there's a very important concept. As long as you apply the same operation on both sides of the equal sign, the equation remains valid. So we'll see how that works right now. Consider 3x is equal to 12. Well, we can see that x is equal to 4, which is a solution to that expression. So let's use that as a test case to see if all operations that we do on both sides of the equal sign will remain valid. So let's suppose we add 7 to both sides. Sure enough, if we add 3x plus 7 and 12 plus 7, on the right side we get 19, and on the left side, 3 times 4 plus 7, and sure enough, it equals 19. So the equation is still valid if we add to both sides. Now, how about if we multiply to both sides? So multiply both sides by 8. So 8 times 12 is 96, and 8 times 3x, if you substitute our solution of 4, so we get 8 times 12, which sure enough is 96. So we've proven that multiplying by the same number on both sides also produces a valid equation. Suppose we were to square both sides, 3x squared and 12x squared. Well, 12x squared is 144, and 3x squared, if we substitute our known solution of 4, we also get 144. So if we square both sides, things still remain valid. So we can use that as a technique to work with our, suppose we inverted both sides, took 1 over 3x and 1 over 12. Are those two still the same? Well, sure enough, 1 over 12 is 0.833, and 1 over 3 times 4 is also 0.833. So we've shown that even inverting both sides preserves the important relationship. So as long as you apply the same operation on both sides of the equal sign, the equation remains valid. Here's the second example, isolating a variable. So let's see if we can use some of the skills that we just learned to help answer these. We're given the formula V is equal to I times R, and we have some test cases of 10 volts and R is equal to 2 ohms. So let's see if we can find the current I in amperes. So we'd like to isolate the I from this expression, V is equal to I times R, which of course is Ohm's law. Well, to isolate the variable I and substitute values for V and R, we need the original formula. V is equal to I times R. We need to divide both sides by R, and you'll see on the right side, the R will cancel out, leaving us with just V over R equals I. So now we can just simply reverse the order. I is equal to V divided by R, and insert the values that we were given and evaluate to find out what the current will be. And sure enough, 10 divided by 2 will give us 5, and volts divided by ohms is the same as an amp, so the answer is 5 amps. Now, here's another example. Remember, please excuse my dear Aunt Sally. So, we have a formula for volume of a sphere, which is V is equal to 4/3 pi r cubed. Now, we have to find the formula for radius r. So, what can we do to both sides of the equation to get r all by itself on one side? The solution is to identify all the operations done to r and undo them one at a time. Alright, so we've noticed that it's multiplied by 4/3 pi, so to undo that, we'll divide both sides by 4 times thirds pi. So we know when we divide 4/3 pi divided by 4/3 pi, it turns into 1, so we'll end up with r cubed on its own. We'll notice that we'll have to do these in reverse order. So we'll have to start looking for addition and subtractions, and then multiplication and divisions, and then exponents, and then finally parentheses. So here we're going to start with the multiplication rather than the exponent, because that'll be the next thing that we do. Now that we have the r cubed is equal to 3v over 4 pi, that's the result of v divided by 4/3 pi. Now we can undo the exponent. So to undo the exponent, we'll take the cubed root of both sides. And the cubed root of r cubed is equal to r. So r is equal to the cubed root of 3v over 4 pi. So let's see if we can use that formula in an example. So suppose we have a spherical tank that must contain 6 cubic feet of liquid. We need to find the tank radius to the nearest tenth of a foot. Well, the solution is to use that formula that we just developed. R is equal to the cubed root of 3v over 4 pi, and substitute in the value for v, 6 cubic feet. Now we need to evaluate that. So we can use a scientific calculator to do that. Multiply first 3 times 6 cubic feet divided by 4 pi. Let's see how we would do that. So first we have to evaluate the fraction. 3 times 6 divided by 4 divided by pi. And we get the answer of 1.43239. Now, how do we get that cubed root? So it's going to be different for each calculator. So let's see how that would work out. We might have an example on a TI-83 series. We have to go to the math menu, press the math button, find the cube root function, and then go back and get your answer to the previous equation, which is second answer. And the result would be 1.127 and so on. Or if you have an earlier TI calculator or some other type of calculator, you might have to find just the root function, the x root of y. So there's probably have a second function, and then you tell it that you want the third root by pressing 3, and it'll take the answer from the fraction calculation and take the cube root of it, and then you get again 1.1272517. Another kind of calculator has the cube root function on the keyboard, and you'd have to press shift to get to that, the cube root function, directly, and then press your answer to get the previous fraction and press equals, and you should also get the same result. So the tank radius, depending upon which calculator that you've got and which method that you've used, the result should be the same. R is equal to 1.1 foot rounded. Now let's look at a more familiar formula. I'm sure that you've seen this one. Fahrenheit is equal to 9/5 C, Celsius, plus 32. Suppose we want to find a formula for the Celsius temperature from this formula. Well, we need to identify the operations, which is done to C, and undo them one at a time in reverse order. First, we'll note that the addition of 32, so let's subtract 32 from both sides of the equation, and the result is that both of these will cancel out, and f minus 32 is equal to 9/5 C. Alright, so we still don't have C all by itself, so what's remaining to be done? Well, we see that multiplication by 9/5, so we're going to need to divide both sides by 9/5, or that's the same thing as multiplying by 5/9, alright? So when 5/9 times 9/5 is equal to 1 times C, and on the left side we have 5/9 times f minus 32. So we reverse the order, and we've got the formula for Celsius temperature. Let's try it out. In example 6 in the book, it says Fahrenheit is equal to 36. So substitute 36 for Fahrenheit and evaluate what's in the parentheses first, and we end up with 2.22 rounded. Let's look at isolating a variable in a more complicated expression. With the lens formula, 1 over f is equal to 1 over p plus 1 over q, and we're asked to find the image distance. Well, we need to perform the operations necessary to isolate q. So first thing we'll do is we'll notice the addition of 1 over p to the term with a q in it. So we'll subtract 1 over p from both sides and then simplify. So 1 over p minus 1 over p on the right side is 0, so we're left with just 1 over q, and then on the left side we have 1 over f minus 1 over p. Now, with so many different denominators, how are we going to get that q up at the top so we could say q equals? Well, one technique that we use is to multiply both sides by all of the denominators. So if we multiply fpq on the left side and fpq on the right side, we'll notice that the q over on the right side will cancel, and we're left with just fp, and then on the left side, we'll multiply fpq to both terms, so we have fpq over f, and the f's will cancel, so we're ending up with just pq on that side. And then the second term, fpq over p, so we're just left with fq. So we end up with pq minus fq equals FP. So I hope you're not getting intimidated by all of these letters floating around here. They're just taking the place of numbers. Note that Q multiplies both terms on the left side, so we'll factor out Q. So that's a technique we often use in algebra. If the same thing is multiplied by two terms, we can factor that out outside of the parentheses, and we have P minus F equals FP. So now to isolate Q, we have Q multiplied by this expression, P minus F, so we can divide both sides by P minus F, which will cancel the P minus F on the left side, leaving us with just Q, and on the right side we have FP divided by P minus F, and so we've done it. We've isolated the Q in that complicated expression. So let's see if we can try it out with some numbers now. So suppose we have to find the image distance Q when F is equal to 12 millimeters and P is equal to 15 centimeters. We can use our derived formula for Q instead of having to put it into the complicated formula and try to isolate the Q value. So we'll just substitute it in, but first we need to convert F to centimeters because we can't mix centimeters and millimeters in the same expression. So we'll multiply by our unit ratio of 1 centimeter over 10 millimeters, and you remember how we did that in the previous module? And we end up with a focal length of 1.2 centimeters, which you probably already knew, which is the same thing as 12 millimeters. Next, we substitute the values into the formula and evaluate. So we'll substitute 1.2 centimeters for F, and 15 centimeters for P, and 15 centimeters for P, and 1.2 centimeters for F, and evaluate that, and we end up with 1.3 centimeters rounded. Now, why did we go through all of that trouble for solving for Q? Why not just substitute the values for F and P? Well, in general, you will encounter many formulas of this form, so this exercise is very helpful for us. We'll often see formulas that have 1 over A is equal to 1 over B plus some 1 over C, some three variables, A, B, and C. And if you want to isolate one of those, this technique that you learned today will allow you to do that. So you can always solve for A, B, or C now, like by using these techniques. As we saw, A is equal to BC over B plus C. We can solve for B. B is equal to CA over C minus A, or we can solve for C, and we'll end up with C is equal to BA over B minus A. And you'll notice that these two look an awful lot like what we saw before with our FP and Q expressions. For example, and you'll see this later on in this exercises, that the equivalent capacitance, C sub E, of two capacitors, C1 and C2, is given by this expression. 1 over CE is equal to 1 over C1 plus 1 over C2. Can you quickly write expressions now for C sub E, C1, and C2? Sure you can. You have the pattern right here, and you can take each location and match it up with this pattern, and you can write an expression for each of those. Why not just solve an equation? Just put the numbers in it and evaluate it. Well, sometimes that is the best technique to use because when you only use an expression one time, it's easier just to go in and substitute the values in and determine the answer. But you still have to use your order of operation. So for example, we have a plastic rod with this expression here, n sub 1 over s sub 1 plus n sub 2 minus s sub 2 is equal to n sub 2 minus n sub 1 over r. My goodness, that's a complicated expression. We're asked to find the image position, s sub 2. Now, we can go through lots of gyrations and try to solve that equation for s sub 2, but I think in this case, since we're only going to do it one time, it's easier just to work with the numbers and we can simplify things quickly. So here we substituted the n sub 1 of equal to 1, and n sub 2 is equal to 1.48, and the s sub 1 is equal to 20.0 centimeters, and also the n sub 2 and n sub 1 and r value over here on the right. So now we need to start evaluating. Now we can actually subtract that fraction from both sides, even before we evaluate it, and we'll end up with an expression of 1.48 over S2 is equal to 0.48 over 4 minus 1 over 20, and we pull the units out since they both have units of 1 over centimeters so that we can work with the expression all by itself. and we'll end up with 0.07 times 1 over centimeters. And that's going to equal 1.48 over S2. So if we invert both sides, remember where we learned that we can invert both sides of the equation and it'll remain valid. So we'll invert S2 over 1.48 and invert 1 over 0.07. So we'll isolate S2, and we have 1.48 divided by 0.07 centimeters equals 21.1 centimeters. Now let's return to that opening scenario with that big complex expression and see how we can solve for g sub a. First thing that you can do is reverse the order, so we can get g sub a on the left side, so that'll just help us out on the end. And then we'll divide both sides by r sub 1 by r sub 2 times 1 minus alpha, because that's what's multiplying g sub a. So that'll leave g sub a squared all by itself. And then on the right-hand side, since we've divided g sub l by the same expression, we'll end up with g sub l over r sub 1 r sub 2 times 1 minus a. Now to undo that, g sub a squared, we'll take this square root of both sides. So we'll take the square root of the same number. That squared just gives you the same number. And we simplify and substitute our values in, and we end up with all of those values inserted and come up with the square root of 1.1022, which is equal to 1.05 rounded. So the amplifier gain, g sub a, is 1.05, or about 105%. Now let's look at some of the practice exercises in the back of the book and see if we can put to use what you've learned in this unit. As before, we will not solve every single one of these practice exercises, but just enough to give you some confidence. Let's look at exercise 1. Given the formula n equals c over v and the speed of light, find the speed of light in a glass having n equal 1.5. So what will v be? We have to isolate v. So to find the general formula for v, let's multiply both sides by v and divide both sides by n. Other words, multiply by v over n. And you'll notice that the n's will cancel on the left side and the v's will cancel on the right side, and we'll end up with v is equal to c over n. Substitute the values for c and n and evaluate. And now we've got v is equal to c of 3.0 times 10 to the 8th meters per second divided by the index of a fraction 1.5. And we evaluate that out to 2 times 10 to the 8th meters per second. So the speed of light in this glass is 2 times 10 to the 8th meters per second. Now, for a total hospital expense in exercise 3, you have an expression that has E is equal to the total hospital expense minus D, the deductible, times 1.0 minus P, the percentage that is remaining that the company pays, plus the deductible. And we're asked to find the total expense. So we'll have to go ahead and substitute our values in and operate them in the right order. And what's the first thing that we should do? Now we're looking for parentheses, right? So first evaluate inside the parentheses and the brackets. 5,000 minus 100, which leaves 4,900, and here's another parentheses, and we need to evaluate that right away. 1.0 minus 0.8 equals 0.2, and now we have some more brackets that we still need to evaluate. So we need to evaluate the 4,900 times 0.20, and we get 980. And then finally we get to add the 100, and we get E is equal to 1,080. So the total expense for the hospital stay will be $1,080. All right, so exercise 5 gives us another example of applying the formula. N sub f equals 1.33 and the thickness T of the soap film. A second order reflection appears with a green wavelength, but lambda is equal to 540 nanometers. So what is the estimate of the soap film thickness, T? So we're going to have to get T out of that expression all by itself. So we can substitute values first and evaluate, thinking that we might have to do this only one time, or we can solve for T first. So let's go ahead and solve for T first. This is a good exercise for us here. So we're going to subtract what's added here to the T first. So we'll subtract lambda sub 0 over 2 from both sides, leaving us with 2 n sub f T equals m lambda sub 0 minus lambda sub 0 over 2. Now we need to isolate t, so we need to divide both sides by 2 n sub f. So we divide both sides by 2 n sub f, and we're left with t all by itself is equal to our expression over here. So now we can substitute our values and evaluate. Substitute in n sub f, n, which is the second order, is equal to our expression over here. So now we can go ahead and substitute our values and evaluate. So substitute in n sub f, and m, which is the second order, and lambda sub 0 and lambda sub 0. And we've noted that we do these multiplication first, and then the divisions first, and then subtract, and then divide the 1, 2 times 3, 3, and we end up with 3.0 nanometers rounded. Alright, so here's that expression I promised you. We're going to find the equivalent capacitance of two capacitors that are wired in series using the formula 1 over C sub B equals 1 over C1 plus 1 over C2. So we're looking for 1 over CE. So let's go ahead and substitute the values in. That's one way to solve that. 1 over C sub E is equal to 1 over 2.3 microfarads plus 1 over 6.5 microfarads, and the result of the numbers will be 0.5886, which you can find out with your calculator, and then you have to invert both sides to find out C sub B, because we don't want 1 over C sub B, we want C sub B. So we want 1 over 5,886, and the microfarads come up, and the answer is 1.7 microfarads. So another method is to use the formula that we derived earlier. 1 over A is equal to 1 over B plus 1 over C. So we can use the first option of A is equal to BC over B plus C. Since we have the very first term here, we're looking for the C sub B. So C sub B will equal C1 times C2, the product of the two denominators, divided by the sum of the two denominators. We substitute the two values in, and the result is 1.7 microfarads, just as before. Okay, so that concludes our treatment of Module 3 for this course, and I know that you're going to have a lot of confidence to do a lot of algebraic expressions and be able to manipulate and substitute and evaluate whatever algebraic expression comes your way. And you'll do a lot of that in this courses to come, so I hope that you'll practice these exercises and complete the rest of them on your own. All right, see you next time.